before the introduction, I run a energy and climate policy program, which is a master's level program at John Hopkins University on our DC campus. And we have approximately 75 grad students who focus on the interface of energy solutions to climate change. And in this presentation today, what I'd like to do is focus on how you can include a model on climate change geoengineering. And at the outset, I want to provide a working definition of climate geoengineering. U.S. National Academy of Science, this is a pretty mainstream definition. So it's options that involve large-scale geoengineering of our environment in order to combat or counteract the effect changes in atmospheric chemistry. And we'll look at that in detail in a few moments. Now, I believe that including a module on climate geoengineering in a climate change course is extremely valuable for a couple of reasons. First of all, I think that for better or worse, there is increasing likelihood that climate change geoengineering in some incarnation be considered a viable policy option to address climate change in the future. And the reason I think this is largely out of despair. If you look at a number of recent studies, they've indicated that if all the pledges of the parties to the Framework Convention on Climate Change and the Kyoto Protocol are faithfully executed, now these post-Copenhagen pledges that the parties have made, assuming they were faithfully executed, and that's a big if, obviously, we are still on track for temperature increase by between 3 and 3.9 degrees Celsius by the end of this century. And there are other studies are less sanguine about what's going to happen. And there was a study released by the World Bank yesterday that said that it is possible that we might see temperature increases of as much as 4 degrees Celsius. That's 7.2 degrees Fahrenheit by 2060 under a business-as-usual scenario. And so when we get to those kind of temperature increases, 3 degrees and above, there's catastrophic implications in terms of institutions and ecosystems. You get a 3 degree Celsius increase in temperatures, it could ultimately melt the Greenland ice sheet, for example, and you get 7 meters of sea rise. The good news is it takes 1,000 years for that to happen. The bad news is it's virtually irreversible, and it's 7 meters of sea rise. 3 degrees Celsius increase in temperatures would threaten the existence of as much as 60% of the species that exist on Earth, according to the latest assessment of the Intergovernmental Panel on Climate Change. 3 degrees Celsius temperature increase imperils most of the existing coral reefs. 3 to 4 degree Celsius temperature increases has catastrophic implications for agriculture, especially in highly vulnerable states in the South. So for this reason, climate engineering, which even a couple of years ago was viewed by a lot of people as that crazy uncle that you have at Thanksgiving, that you mutters in the corner and you don't listen to, has now been accorded a lot more credibility, largely because people are extremely afraid of passing critical thresholds within the course of the next 30 to 40 years. And so in recent years, you've seen hearings being held in the United Kingdom and in the United States in Congress and Parliament, respectively. You've seen small-scale experiments in Russia. You've seen the possibility of such experiments happening in the United Kingdom also. The reason I think focusing on geoengineering in one's classes makes sense. This reason is that geoengineering in many ways is a jackpot for helping students in terms of thinking in an interdisciplinary fashion, because it facilitates student exploration of the interface of science, technology, ethics, law, and governance, all in one lecture. And we'll talk a little bit more about it in terms of when we look at governance issues and we look at the discussion questions at the end of this presentation. But it really does let you do all of that. And my experience, and I've taught engineering modules in 5 climate change courses to date, and I've lectured probably 100 times on the topic now. This is something that really engages students It's in our nerdy world, at least, it's pretty sexy topic. Maybe because of the technology, the scope of what it can do, the ethical issues that it raises. I think it's a good topic to engage the students with. So here's what I like to do very briefly in this presentation. First of all, before you can think about teaching geoengineering or look at the kind of questions you want to engage students with, it's important to know what the primary geoengineering options are. So I'm going to talk about those and the broad categories of geoengineering that exist. And I apologize, that will take a while, but I think that, like some of the other lectures we've had in CAMEL that have focused on an entire course, because I'm focusing only on one topic, it's important to really flesh out the particulars of that topic first. Then of all, I want to talk about governance options in terms of geoengineering and what kind of questions you could tease out with students in this context. And then finally, in terms of teaching resources, I want to talk a little bit about discussion questions and possible simulations that one could do in this context. So first of all, let's talk about the geoengineering options that exist. Proposals are generally divided into two broad categories. The first of these categories is what we call carbon dioxide removal schemes, or CDR. What these schemes seek to do is increase the sequestration or storage of carbon dioxide. And by doing that, by taking more carbon dioxide out of the atmosphere, it allows more of the outgoing long-wave radiation to escape back into the atmosphere. And as a consequence, it exerts a cooling impact. It's the same kind of approach that we're utilizing when we try to grow more trees, for example, to sequester more carbon dioxide. And the broad distinction between doing that and geoengineering is the nature of scale more than anything else. The second broad category of geoengineering options is what we call solar radiation management, or SRM approaches. And these approaches seek to employ technologies that deflect incoming solar radiation back to space so they never reach the Earth's surface and exert a warming impact. And as a consequence, again, we help to cool the planet. So with that in mind, let's look broadly at what some of these approaches are and what some of the potential issues are with those. And as we work through these, I think you'll see some of the things that you help your students grapple with in the context of science, ethics, law, governance, etc. First of all, let's look at carbon dioxide removal options. And the primary one that is discussed is ocean iron fertilization. This is one that was in the news recently. Probably many of you saw it. It turns out that in July, a gentleman named Russ George on the coast of Vancouver, a large amount of iron filings into the ocean. And this was a geoengineering experiment. It was billed many things, but at its base it was a geoengineering experiment. And it was utilizing, on a small scale, an approach called ocean iron fertilization, and the idea behind it. So ocean iron fertilization strategies seek to stimulate the production of phytoplankton. And as some of you know, phytoplankton is, hold on one second, I'm having problems getting this slide to go. Phytoplankton are microscopic plants that are found in the world's oceans. And these plants take in carbon dioxide from the atmosphere, and they convert this carbon dioxide to organic carbon. And they use this organic carbon in the photosynthetic processes that allow growth and reproduction of these organisms. This is the organic carbon that is produced in the photosynthetic process, immediately consumed at the surface. These plants, phytoplankton species, are consumed by zooplankton species, who in turn are converted by higher order species. And most of the carbon dioxide is then released back to the surface of the oceans, converted back to CO2, and ultimately ends up back in the atmosphere. So you don't get a lot of sequestering at that point. However, a small portion of the remainder of the carbon that is sequestered in these organisms is effectively removed from the system and transported to the deep ocean for storage when the organisms die. And this is a process called the biological pump. Some of these organisms are not consumed at the surface. When they die, the organic carbon, the CO2 that's been converted to organic carbon is still inside those species. They ultimately die. They drop to the bottom of the ocean. And the idea is that now you have CO2 that's sequestered and will not be available to the atmosphere for at least 100 years. What some researchers have argued is we should seek to stimulate the growth of phytoplankton as a way to reduce concentrations of CO2 by enhancing sequestration via this biological pump. Now, where is this? Well, from say there's certain areas of the world's oceans, probably the Southern Ocean, areas around Antarctica, the high levels of major macronutrients that are critical for phytoplankton, especially phosphorus and nitrogen. However, they have low levels of a critical micronutrient, which actually it helps to suppress production of phytoplankton. That micronutrient is iron. And this iron deficiency, it's argued, severely limits phytoplankton production in these areas. So opponents of ocean iron fertilization, such as Russ George, argue that introducing substantial amounts of iron into these areas to supplement natural supplies will stimulate phytoplankton growth, which in turn will suck in more carbon dioxide, and in turn will ultimately result in the sequestration of more of this carbon as these species die and drop to the bottom of the ocean. And their proponents are very high on this approach for a couple of reasons. First of all, they claim that ocean iron fertilization could sequester as much as 25% of the world's carbon dioxide by the year 2100. That would obviously be a large wedge of what needs to be done from a policy perspective. So they argue that ocean iron fertilization techniques would be extremely cheap, cost about $2 to $5 per ton of carbon that would be sequestered. If you had in perspective, many of the approaches that we're looking at to mitigate climate change, carbon dioxide emissions, are in the range of $30 to $45 or higher. So that this would be an extremely inexpensive and extremely effective approach. And this is kind of a mantra for climate change geoengineering in general. There are questions associated with both effectiveness and the safety of going down this path. First of all, in terms of effectiveness, one that we know from a scientific perspective is phytoplankton will only remove carbon dioxide from the air permanently if they ultimately die and sink to the bottom of the ocean. Okay, and one of the things that we're increasingly seeing as we start to conduct experiments in this context is that most of the phytoplankton indeed are consumed by zooplankton well before they get to they die and end up at the bottom of the ocean. So it's extremely questionable whether this would occur. Additionally, much of the organic carbon found in these phytoplankton species, even when it is remineralized by bacteria, they inorganic carbonate and bicarbonate during the first 500 meters of the sinking process. And as a consequence, it ultimately results in a release of or a conversion back to carbon dioxide, which ultimately ends up in the atmosphere. So disconnect to some degree between the theoretical models in this context and what we started to see in terms of small-scale experimentation. And for those of you who have students on the science side, it's a very interesting sort of issue to discuss. As models of potential for ocean fertilization become more sophisticated, prospects for it became less hopeful. 3 of the 12 iron addition experiments that have taken place to date have shown any sequestration of carbon dioxide. And a couple recent studies have indicated that at most a reasonable distribution of iron would probably only reduce atmospheric concentrations of CO2 by about 10%. And one study from Ohio University said even if you fertilize the entire 20% of the oceans that are low in iron, you only reduce concentrations of CO2 by about 38 parts per million, which is, if you buy that study, is much less than a 10% reduction in terms of what we anticipate by the year 2100. There are potential negative ramifications of ocean iron fertilization. As all of you know, we're talking about ocean ecosystems. And ocean ecosystems are extremely complex. And when to produce, assuming we can produce more phytoplankton in the oceans from ocean iron fertilization, we get to pick and choose what phytoplankton we get. And the threat is that we may get a plethora of phytoplankton species that may be undesirable for the food web or maybe even toxic. In one ocean iron fertilization study, abundance and biomass of one phytoplankton species, a species called Cystis antarctica, increased substantially. And species proved unpalatable to mesozooplankton species in the region. And a number of researchers had concluded that if there was a massive proliferation of that species in that area in the oceans, it could have wreaked havoc with the food web in that area and created a trophic cascade where mesozooplankton species would no longer have food availability, and it would impact species above them food chain. It's possible that ocean iron fertilization could result in widespread eutrophication. That's the proliferation of algae that choke off light to species and create algae blooms. And paradoxically, ocean iron fertilization could exacerbate climate change. Because phytoplankton begin to die and decay, it results in a substantial increase in consumption of oxygen through the respiration process. And this could result in anoxic or oxygen-deprived dead zones in the oceans. And beyond lots of species, anoxic environments produce lots of methane and nitrous oxides. And as you know, these are extremely potent greenhouse gases. Methane has the global warming potential of 21 times that of carbon dioxide. Nitrous oxide's 206 times that of carbon dioxide. And so a couple of studies have concluded that ocean iron fertilization might result in an increase in warming as a consequence of these impacts. Okay, the other primary carbon dioxide removal scheme is air capture. And the air capture technique is to capture carbon dioxide from the air directly, any source, the use of either sorbent materials such as calcium hydroxide or calcium oxide. You can see this on the right side of this picture. These are what David Keith at Columbia calls artificial trees that would use these surfaces to essentially suck in carbon dioxide. A filtering system, as you can see on the right side, that would force air through the system and in turn would filter out the carbon dioxide from the atmosphere. This is air capture. Persons argue they could sequester enough carbon dioxide through this air capture process to return atmospheric concentrations of carbon dioxide to pre-industrial levels if we wish to. So we get back to, for example, 280 parts per million, and probably the proponents argue reduce temperatures back to pre-industrial levels. So potentially an extremely effective sort of process. Obviously does not have the impacts in terms of ocean ecosystems that we talked about. However, there are some extremely serious issues associated with the viability of this process. First of all, a number of recent studies have indicated that this process could cost as much as $600 per ton. Okay, that obviously would make it non-economically viable compared to mitigation options that we're looking at right now. Opponents, on the other hand, say that we could bring the cost down ultimately to only about $25 to $30 per ton due to both economies of scale and the possibility of using carbon dioxide that we extracted to feed algae to produce fuel, for example. And so it's argued it has to be entered into the process. Somebody has wait one second there. Sorry, that somebody annotate that slide at that point. Another problem associated with air capture is that you would need ultimately to store the carbon dioxide. It just doesn't get quote unquote thrown away. You either have to sequester it underground or sequester the carbon dioxide in the oceans. And in order to do this on the scales that we're talking about, you would need massive infrastructure. It's been estimated that you would need as much piping, for example, to pipe the carbon dioxide that would take out of the atmosphere and ultimately convert to a liquid. You would need much piping as the oil and natural gas industry combined currently utilize. And obviously, not only is that going to have a huge cost, but probably going to have NIMBY problems in my backyard, political issues associated with this. And it's an interesting issue to discuss with students in terms of what would reconcile interests of local communities and a technology of this nature. Okay. Very quickly then, the second of these broad categories is solar radiation management geoengineering approaches, or what we call SRM. And the primary SRM proposal that is on the table these days is stratospheric dispersion of sulfur particles. The idea here is to disperse a huge amount of aerosols, such as liquid sulfur dioxide, in the stratosphere to reflect into solar radiation back out into space. The sulfur dioxide aerosols have what we call high albedo, meaning a very high reflectivity for in-solar radiation. And so the idea is that it would create this huge reflective blanket in the stratosphere, would reflect a lot of incoming solar radiation back out into space, exerting a cooling impact. In parlance of climate science, this would reduce insolation, that is, decrease the amount of solar radiation received on the Earth's surfaces. And a number of recent studies have said that we could reduce insolation at least 1.84%, which would allow us to decrease temperatures back to pre-industrial times again, as if we had atmospheric concentrations of carbon dioxide of 280 parts per million, even though the amount of carbon dioxide in the atmosphere may actually continue to increase during the time that we deployed this. And has included that we would need to introduce about 5 trillion grams of sulfur dioxide aerosols into the atmosphere to offset the warming impacts of a doubling of atmospheric carbon dioxide levels from industrial levels. And this is the study that shows what that impact would use. If we do this, how would we deliver this amount of sulfur dioxide? Well, there's all kinds of options. We could do it through aircrafts, planes. We could use unmanned airships, such as the U.S.'s Department of Defense's high-altitude airship, and we would send a pipe from it and or a hose, and simply disperse the sulfur dioxide in the atmosphere. The best of this approach are again reflect some of what we talked about in terms of ocean iron fertilization. First of all, it could be done. Its impacts would be very quick. We know this because we had a volcano in 1991 called Mount Pinatubo, which, by God, released about 5 teragrams, 5 trillion grams of sulfur dioxide, and a substantial decline in temperature over the course of the next year. So, we had a large-scale inadvertent experiment of this context. And to cite that, as shown that this approach would work. They also indicate that it would be about 100 times less expensive than the same cost of mitigating in terms of reducing carbon dioxide and getting the same kinds of impacts. So a lot of bang for the buck. Now, there are potential downsides to this approach, and these are quite substantial. First of all, stratospheric sulfur dioxide injection could substantially increase aridity or dryness in some parts of the world. Many researchers have predicted that it could alter the hydrologic cycles in the tropics and would result in large decreases in precipitation over vegetated surfaces in Southeast Asia and Africa. Southeast Asia, for example, could shut down the monsoon from time to time, which would threaten the food supply of 1 billion or more people. And the proponents of geoengineering cite Mount Pinatubo as empirical evidence that this approach could work. What is conveniently not mentioned sometimes is that after Mount Pinatubo exploded, we saw the lowest stream flow of the Ganges River in history, the lowest amount of precipitation in recorded history. And so probably some empirical evidence also that this approach could have this kind of impacts. Another potential negative impact from this approach is in terms of ozone depletion. Because this approach would cool the stratosphere by deflecting more incoming radiation back out into space, it accelerates the process of the breakdown of the ozone layer by the ozone depleting substances that we find in the atmosphere, and estimated that it could substantially diminish the ozone layer in the Antarctic vortex, and it also delay recovery of the ozone layer, had been devastated by ozone depleting substances and is now starting to rebuild as a result of the Montreal Protocol, the international treaty that we had to phase out substances. It delayed that recovery by 50 to 70 years. On the other hand, proponents say that you would attenuate incoming ultraviolet radiation from the sun because of the dispersion of these sulfate aerosols, and that would offset the potential impact in terms of ozone impacts, ozone depletion impacts. So it remains out in this context. Potential impacts: you could introduce a lot of sulfur dioxide that would fall into the stratosphere, where it would become a poison, as is true with sulfur dioxide currently that we get from power plants and other sources. Potential pollutant impacts. You have a threat of what's called the termination effect. If you employ this technology, and let's say carbon dioxide levels and other greenhouse gas levels can increase because people decided, well, we don't have to really decrease these emissions now because we have this protective blanket. If you were to do that and then had to stop using this technology, and this would happen for a couple of reasons. One, let's say India, for some reason, thought it was unreasonable that you shut down their monsoon and threaten nuclear war if you didn't stop deploying sulfur dioxide particles. It might compel a nation or a group of nations that were deploying this approach to stop. Or the technology might fail. We've owned small-scale experiments with this. We know what happens with sulfur dioxide in the atmosphere over the course of a short period of time. But a longer period of time, there may be feedback mechanisms we don't understand that would undermine the effectiveness of these particles in the atmosphere. So if these approach suddenly didn't work and we had a buildup of greenhouse gases in the atmosphere, what's called the termination effect. Evidence study says that if you were to terminate use of these technologies or the technology failed, see a 3 to 4 degrees Celsius increase in temperatures in 11 years, or 6 to 10 degrees Celsius increase in temperatures in 20 years. And to put this in perspective, the temperature increase that's 20 times more rapid than what would happen under a business as usual scenario. So that obviously is extreme risk associated with this technology, and it leads to interesting questions with students that you can ease out in terms of weighing risks associated with business as usual scenarios with climate change as opposed to these alternatives, and looking at the risk associated with the translation effect and deciding how, as a policymaker, one would tease those out. The primary SRM option that we look at is something called cloud seeding. Cloud seeding seeks to increase the number of water-based nuclei, or water drops in clouds. And as a consequence, it would brighten the clouds, it would increase their albedo, or reflectivity, and to deflect more incoming solar radiation back out into space. The proponents of this have proposed using remote-controlled, driven spray vessels to simply seed maritime clouds with water particles. Now, this approach obviously wouldn't pose the threat of ozone depletion, but again might alter precipitation patterns around the world and hence exert danger. And the finer SRM approach that we look at are space-based. These include using refractive screens that would be synchronously orbiting the Earth to deflect radiation back out into space, or a huge amount of reflective disks to do this. The most challenging part of this approach would require you to have about 5 to 16 billion with mirrors, and it would cost more than $5 trillion. And that's something to be teased out. In terms of governance implications, the last primary thing I'll talk about, this is an area where I think you can really get students to grapple with a vision of what it would look like to establish a program to research geoengineering options and perhaps ultimately deploy those options. One of the things you can ask is, do we even have a research and development program? And most students will recoil in horror when you talk about that and say, no, we shouldn't do that. We should be seeking to mitigate our emissions and not get one of these fixes. But one thing you can do is press students on this point and argue, could it be possibly worse to not research these options? Because if we don't research them, it's possible that in the future we're going to have one of those moments where we say, oh my God, we're going to pass critical thresholds. We better just try to deploy one of these technologies quickly. And the argument that's made by support research is, if you don't reach the options now and tease out what are the ones or the not so bad ones against the ones with potential catastrophic implications, then you may make some very bad decisions with panic in the future. And so it's better to have a research program in place. And I've seen students really grapple with weighing those values and the possibilities of those things happening. Another argument that could be made is if you have a research program now and you bring in stakeholders from around the world to engage in this research, you can help to develop some norms that ensure that if you ever do ultimately deploy technologies in the future, that you have more input from stakeholders and you have more sense of developed norms to not allow potentially seriously detrimental technologies to be deployed in the future. You can talk to students is, what would the governance mechanisms for research and development approaches look like, or deployment? You can look at the various regimes that could govern climate geoengineering. The Convention on Biological Diversity, for example, has been looking at ocean iron fertilization. The International Maritime Organization has also been looking at ocean iron fertilization, has been talking about and has been developing risk assessment protocols, for example. The Framework Convention on Climate Change, a logical one to potentially govern these things. So the things that you can talk to with your students is, would it make sense for us to allow fragmentation? It's better to have a number of different regimes governing this. You get more innovation that way, more input into the process from a broader stakeholders, or are you going to create endless confusion and the potential of some of these technologies falling through the cracks in ways that you don't want them to. It's a good way to introduce students that might not spend a lot of time with the law to look at those kind of issues. Another thing is that it's a good way to get students to look at the text of treaties, which they're often, if they're not law students, and quite frankly, even sometimes when they are law students, is an intimidating thing to do. How to read treaties. Well, give them a live sort of issue to look at. I find that they'll delve into treaty language more, and they can get quite creative. I can break students up into groups to answer questions of this sort about treaties and give them the raw text. And one is a good example. One of the things you can ask them is, if you decide you want to let the Framework Convention on Climate Change govern geoengineering, would it even have legal jurisdiction to regulate solar radiation management techniques? And the argument that you can make here is that if you look at the treaty, it really talks about stabilizing greenhouse gas concentrations, right? And it talks about mitigating climate change by reducing emissions, right, and removing them by sinks. Well, a carbon dioxide removal scheme, a engineering scheme, clearly regulated under the Framework Convention, right, because it's really a removal or it's a creation of a sink. But some radiation management approaches don't seek to reduce the amount of greenhouse gas emissions. They seek to simply deflect more of the radiation back into space so it doesn't get trapped by those greenhouse gases. Because then the Framework Convention doesn't have the ability to regulate these kind of approaches. On the other hand, Article 3 of that treaty talks about requiring parties to protect the climate system in terms of how they address climate change. So would that mean that all of the geoengineering approaches would arguably fall under the regulatory rubric of the Framework Convention? And it gives the students a way to grapple with and interpret it. You can also seek to tease out the research programs. How much buy-in would we require by countries? What would be good models for international research consortia at this point that might apply in the context of this? Genetically modified organisms, for example, nanotechnology, etc. To bring in a broad array of other technical approaches and see if they're relevant in this case. You talk about procedural issues. There are international treaties that allow you to assess the potential transboundary impacts of a technology that you might seek to deploy. We employ that in this case. If we did it, who would be relevant stakeholders in this? Who gets to provide input into the process in terms of those potential transboundary impacts? And the veto, I think it's going to adversely impact their interests. Can they stop the technology from being deployed? Are we going to require a supermajority? Are we going to acknowledge that some country may be injured by this, but they still desirable for good of the whole? You can get all kinds of moral and ethical issues in this context. And then finally, you can talk about liability regimes. If people are potentially going to be imperiled in South Asia by deploying these technologies, should we compensate them for the damages? You can imagine other issues you can help students grapple with there. What would be some of the challenges to establishing that kind of liability regime? How do you establish causality, for example? The monsoons are weakened from time simply by natural variability in the atmosphere. So how do you know when a geoengineering approach has created those phenomena and when it's natural factors that have done it? And what does that mean in terms of compensation in any given year? Who pays for this kind of compensation? Is it the world community as a whole? Is it the countries that deploy the technologies specifically? Are it the countries that benefit the most from these technologies? Do we have the same principles of common but differentiated responsibility that we apply under the Framework Convention? Countries might seek damages, have those damages offset by the benefits that geoengineering approach potentially confers. For example, there's lots of evidence that a business as usual scenario in terms of climate change will imperil the monsoons in Asia and result in a big decline in precipitation. So could a country that deploys a geoengineering approach argue that before you seek damages, you have to acknowledge that we're benefiting you, and as a result, it reduces the potential damages that that you could get from this approach? How do you suss out those issues? It's things that students like. Okay, and so we're running out of time, and so the last thing I'll do is I'll just very briefly talk about some of the discussion questions that I use in classes, and these discussion questions are going to be posted by the CAMEL folks in the next couple of days. Some of the questions you can ask is, aren't we already engaged in geoengineering the climate by failing to arrest our greenhouse gas emissions? And so from a moral or legal perspective, is it fundamentally different to simply do intentionally now instead of utilizing geoengineering? Is a so-called moral hazard objection to geoengineering that some people advance, which is that if we deploy geoengineering, people will take their foot off the pedal in terms of reducing their emissions because they think they need to do it anymore. Is that a legitimate issue? Or do we acknowledge the fact that the world community isn't doing much about reducing its emissions anyway, and so it's a bit of a red herring? It's a good sort of issue to suss out with students. If we agree that countries can utilize geoengineering, which countries can utilize it? Should most vulnerable countries in terms of climate impacts be given carte blanche to do this, as opposed to countries who are supposedly engaged in sub-luxury greenhouse gas emissions, such as the United States or the European Union? If a private actor, such as George, the gentleman off the coast of Vancouver, engages in these kind of activities outside of the national jurisdiction of any country, is there a way that we can regulate those kind of things that are under the law? And it gives an opportunity to give the students the trees that might be relevant and see if those provisions would apply. And it gives them a good lesson, too, in terms of how supple the kind of agreements can be. And so, again, a good gateway for students into law and policy. And okay, with that, I'm going to stop and ask if there are any questions about these issues, and hopefully I'll be able to find my way back to the chat site at this point. Okay, I see the chat site, so hopefully, if there's questions, one can put them in here. Oh, one question is, can you go over again the magnitude of the termination effect for sulfur dioxide injection? Yes. A number of recent studies, and it should be emphasized that they're contested, as is most of the things here, which again is why it's fertile ground, really good fertile ground for having students grapple with the science. But there have been a number of studies that have said that if, assuming, for argument's sake, that countries don't substantially reduce their greenhouse gas emissions during the time that we deploy sulfur dioxide injection, after even a course of 2 years, for example, you could see a substantial termination effect. So within another 20 years or so, you get temperature increases in some parts of the world, for example, in the northern hemisphere, as much as 6 to 10 degrees Celsius over a business as usual scenario. So that's 20 times greater than what would happen if we really allowed greenhouse gas emissions to increase apace. Because what happens is you get a massive pulse of forcing associated with this that had been masked during the entire time. And from the standpoint of the ability of species, for example, to adapt, or human institutions to adapt, it's likely that those kind of systems would be overwhelmed by that sudden onslaught of temperature. And the other implication from the standpoint of governance and also from a standpoint of morality is you would have to continue to deploy this kind of technology for hundreds of years, probably. And so you're establishing a governance regime that needs to be resilient to a degree that we have never heretofore created in terms of the world community. Okay, just looking to see if there's any other questions. I'm not seeing any right now, but we can wait for another minute or so, and then we'll wrap up. What are student discussions about the reality or otherwise of moral hazard? What do you think? It's a good question. First of all, I'll tell you what my students usually say. Most of my students take the position that we're so little, it's not going to make a substantial difference if we're deploying geoengineering. I find a lot of my students resistant to using geoengineering because of some of the potential negative impacts, but terribly concerned about the moral hazard issue. As sanguine in that context, I think that students often are overly pessimistic in terms of what we're doing. I mean, we undoubtedly, in terms of the pledges that were made after the Copenhagen conference, are not doing enough. It was a substantial gap in terms of gigatons between what needs to be done to not pass the 2 degrees Celsius threshold, right, that scientists tell us is when things really become frightening, and what's been pledged. It's probably somewhere between 9 and 12 gigatons at this point of carbon up until 2020 even. On the other hand, we're doing substantially more than we were in the past. We're starting to engender participation by developing countries, and even though their commitments have a lot less legal import than those of the developed countries, nonetheless, we are starting to make those commitments where we're getting almost universal commitment to reducing emissions by both major developing and developed countries in terms of emissions. And so I do think that there's a threat that they could pare back their commitments. And if one of these geoengineering technologies were proven to be successful, at least in the short term, and that could imperil efforts in the longer term to address this issue. And one of the things that I didn't say, but is clear, is that even if you deploy these technologies, such as solar injection, and they're successful in the short term, only if you allow greenhouse gases to continue to increase the pace in the atmosphere, it will overwhelm those technologies, and they will be unveiling or at least will only mask a small amount of what would ultimately happen. Now, we may be able to policymakers that that's true, and so they understand that this is truly only a bridge to a decarbonized future. But I'm not so sanguine when it comes to politicians, especially in countries like the United States, where the decision-making horizon seems to be, 2 years for people in the House of Representatives, 4 years for president, 6 years for people in the Senate. And so I'm not certain that I want to provide any alternative that provides any potential inducement to dial back on what are arguably going to be tough political decisions in the future. Let's see. Let me back up here in terms of the question here. What are the most serious negative concerns and which nations would they affect? Jim Hansen's already pessimistic about greenhouse gas reduction, advocates breeder reactors. Right. In terms of the negative impacts, if you look at, it's a little difficult to assess. It depends on what technology you're looking at. If you're looking at ocean iron fertilization and potentially negative impacts on ocean ecosystems, it may be countries that are most dependent on fisheries, for example. So it could be some large fish nations, it could be some small island states, etc. Looking at precipitation impacts in terms of sulfur injection or cloud brightening, it looks like the primary impacts would be in the Amazon, especially in the northern parts of the Amazon, in sub-Saharan Africa, and in Southeast Asia. But again, one of the dilemmas that we have, or one of the problems that we have, is that to make these assessments, we're using regional general circulation models, same GMs that we use for climate change predictions. And as all of you know, they are extremely granular at this point. Our GCMs do a pretty good job of predicting what will happen on broad scales, but when you get to the subgrid levels, regional levels, they've proven to be notoriously inaccurate at points, and there's more reason to believe that they're more accurate in terms of making assessments of what geoengineering deployment would mean. And so that's a major area of uncertainty. And again, tease out with students, how do you make decision making in an era of huge uncertainty in terms of in the background, what will happen in terms of climate change, and then in the foreground, at least for this module, what will happen if you deploy these kind of technologies. Termination effect seems to be a deal breaker. Well, yes and no, for a couple of reasons. First of all, some proponents argue that the termination effect won't happen, and I won't go into great detail because we're truly running out of time now, but I can cite people with sources where they argue that we wouldn't get the kind of pulse that people are talking about. Second of all, some people are arguing for a more measured approach, and what they're saying is, let's not try to return temperatures back to pre-industrial levels. Let's just use enough of this sulfur dioxide to ensure that temperatures don't increase to more than 2 degrees Celsius. In other words, the guardrail that we've talked about. And one of the benefits of that approach, there's a couple of benefits they argue, is first of all, that means you'd have to inject a lot less sulfur dioxide into the atmosphere, which means that there's a lot less danger of the negative precipitation impacts that we're talking about. Second of all, it would ensure that the termination effect wouldn't occur because countries would realize that they had to continue to reduce their greenhouse gas emissions because if they didn't, the geoengineering system would be quickly overwhelmed by the increase in carbon dioxide. So in some ways, it would send a clear signal that truly was a bridge and not a fix that would allow countries to get off of the hook. And so that's how many of them get around the nation effect. Okay. Question was, the negatives and uncertainty sound so overwhelming. Do you yourself think mitigation and conservation are the best approach? Yeah, I get this a lot when I do these things. I wish I had a definitive answer to this. I have to say there's days I wake up and I look at what the world community is doing, and I look at this study that I was talking about a couple of days ago, the World Bank saying 4 degrees Celsius by 2060, and think about what the world would look like and say, my God, we may have no alternative but look at these approaches. And it might make sense for us to be focusing our efforts on the approaches that seem the most benign to see if they have potential. For example, air capture has very few negative impacts. If you can, and it is a big if, but if you can figure out a way to sequester all that carbon dioxide or use it for algae production to use in biomass fuels, then you don't have the threat posed with sulfur dioxide injection or potentially imperiling the world's ocean ecosystems, and it might make sense to be looking at those. I also probably come down on the side of people who believe that you do need to do the research and development, because otherwise I think there will be a, pardon my French, an oh crap moment in the future where we deploy one of these technologies without really having thought about it. And as we saw with Russ George, an individual can do this. And that's not purely in the realm of the hypothetical. Both Richard Branson and Bill Gates are funding geoengineering technology at this point. And you could easily see a billionaire in the future with a Messiah complex believing that they should deploy one of these technologies to quote-unquote save the world. And so I think it's important for us to probably assess these options, discount the ones that are wholly Strangelovian at this point, and try to develop norms for the world community to determine how we would regulate these technologies if we were ever decide to go down that path. Loads of governance, stakeholder, international negotiation issues, almost mind-boggling. Yep, that's one of the reasons that it's fun to teach. Economics, trade, ozone layer. Yep, it is a panoply of issues that you could take on. Would have to be addressed. And my friend Andy Strauss, who's a law professor, one of the questions that he asks when he teaches this is, given that fact, do you need an entirely new sort of world community instrument to be able to regulate something of this magnitude? And if yes, what would it look like? And that's a good question to work out with students. And it's good to segue into whether climate change itself requires a different kind of governance mechanism that encompasses the panoply of sectors that you talked about here, economics, trade, etc. Let's see. Skeptics say that nature will take care of itself. Are there skeptics among students? Well, that's a great question. I mean, that goes beyond geoengineering. It's one that gets me on soapbox. I find some professors, especially law professors, who are people that I deal with a lot, almost contemptuous of dealing with arguments of climate skeptics, and they say I won't even address those issues in class. The opposite. I actually have a full class looks at the 10 primary arguments that I can suss out by skeptics, and then seek to outline from a scientific perspective why I think that those arguments are either not correct or they're overplayed. And the reason is I think in any given class in most schools, you have a substantial number of skeptics. And if you simply dismiss their arguments as relevant, you haven't, quote unquote, won them over, haven't engaged in the kind of colloquy that engages learning. The other thing is that if you believe in climate change and you think we're developing citizens that will go out there and engage in these issues and help convince other citizens that we need to do something about this, you're not doing them any favor. Because if they haven't grappled with the arguments of the skeptics and they go up there in that forum, there will be a lot of skeptics who have done homework that will clean their clocks out. And I've seen that in public forum. For example, Chris Matthews on Hardball has had climate skeptics on, and he doesn't know crap about climate science. He really doesn't. And these guys embarrass him. They answer arguments that he has no way of responding to. And that he's done best by actually knowing what those arguments were and what some of our responses are. So yeah, I think you really have to address those issues. Probably not here in the geoengineering module, but early on in the climate change course. And it's another good way to admit, because you have to if you're honest on this, right? The massive uncertainties that we have about potential impacts in the future and how these scenarios will evolve, and say how in an environment of uncertainty do we make a policy? How do we do it in other contexts? What are the relevant metrics here, and what does it mean in terms of how much we should expend in terms of resources? What are the opportunity costs of doing that? The Warren Lomborg sort of arguments. And I think you get some really good discussions with students, and they respect you more for not, quote unquote, hiding the ball on these issues. Any reduction of light energy to Earth would reduce photosynthesis, which would then reduce carbon dioxide absorption. Are there models to predict the balance of light reduction to carbon dioxide increases? It's an excellent question. There are some early efforts to do that. There's a couple of researchers in India that are looking at that. I don't believe that they have any of their research to date. So it's an excellent question. It is one that you will see research on. I mean, one of the things that happened in this field is 5 years ago, if you looked up geoengineering in terms of peer-reviewed literature, there was virtually nothing. Now there's quite a proliferation of it, and that is one of the issues that is being looked at. Okay, thank you very much. I really appreciate your attendance. I appreciate the questions, and should you have any additional questions in this context, please feel free to contact me. My email is wburns@jhu.edu, and I really apologize. I forgot to put that contact information in, but it's wburns@jhu, Johns Hopkins University.edu. And once again, thank you very much, everyone, and have a great Thanksgiving. Goodbye now.